Hello everyone, good afternoon. Sorry for the delay. I was stuck up in the traffic jam and I'm coming from Ghaziabad. So I stay there and from there I have to come to the Rajendra Place classroom there. And today it was a very heavy traffic. So I informed the batch coordinator that please convey this to students that I may be late for the class. So I am here and you have got one document. I am getting that document downloaded on the iPad. I have shared with you one document on nuclear science and technology. There is a handout on nuclear science and technology, right, which is a 4-5 pages document with the DAE, Department of Atomic Energy Facilities and all this one. And since today we are going to start with the new topic of nuclear science and technology, so I have provided a supplementary material. As you know that every topic, right, when I started with the space science and technology, I had given you certain handout there, right, 2 handouts you have got there. Same way nuclear science and technology, I have provided you a handout. What will happen? All the respective topics which require the understanding from some theoretical point of view, I will be providing you the handout on that, right. So today since we are going to start with nuclear science and technology, so I have provided a handout from the Vision IAS material, Mains 365, that is compiled from Mains 365, and we will have a discussion in the classroom. So I request all of you who are present live in the classroom, kindly download the document, right? Kindly download the handout, so that when I'll come to the handout, I will mark important points. So you can also understand and underline in your soft copy whichever areas I will highlight in my iPad, which will be seen to you, right? So please download and keep it there. I will come to the handout in a little while, right? Now nuclear science and technology, if you see the development part of it. So nuclear science and technology here, in terms of nuclear science and technology development in India, the role of Department of Atomic Energy comes there. And you all know that Department of Atomic Energy, DAE, comes under Prime Minister Office, right? It comes under Prime Minister Office, the PMO, right? Now DAE, Department of Atomic Energy, there is under this you have an Atomic Energy Commission. Atomic Energy Commission is there, right? Atomic Energy Commission, AEC. Now Atomic Energy Commission, just like a Space Commission, I have already said, in India for space matter we have a Space Commission. Similarly, for any atomic energy, nuclear power development, we have a dedicated Atomic Energy Commission in India, right? And there is a chairman. There will be a chairman who will look into all the policy matter. And the chairman comes from scientific field, right? He or she may be a scientist who has worked for 25-30 years in the field of nuclear technology, and that person gets the chance to become the opportunity to become a chairman of Atomic Energy Commission, right? You all know the first chairman of Atomic Energy Commission was Dr. Homi Jahangir Bhabha, right? He is the founding father of Atomic Energy Program in India. So the first chairman, he became there, and then subsequently there were number of other chairmen who took over the in charge and helped in development of nuclear technology in the country, right? Now when we talk about scientific organization, within this you have a scientific organization there, right? There are various scientific organization and institutes which work in different fields of nuclear technology. Let's say you all know that BARC, Bhabha Atomic Research Center, that is in Trombay, that is a part of Chembur in Mumbai, right? Trombay, Chembur area, that is in part of Mumbai, and it also has a center in Tarapur. Tarapur and Trombay both are coastal sites, right? So Trombay, and there is another one in Tarapur. Tarapur is on the way to Gujarat. When you move from western side from Mumbai towards the Gujarat side, Valsad, right? Palghar, West Valsad. Near to that there is Tarapur Atomic Power Station, TAPS. So BARC is primarily where Trombay in Mumbai, and then there is another subsidiary center in the Tarapur, that is in Maharashtra only, when you go towards the Gujarat side. Apart from that, there is another center called IGCAR, Indira Gandhi Center for Atomic Research. What is the full form IGCAR? Indira Gandhi Center for atomic research, that is in Kalpakkam. Kalpakkam is a place, again a coastal place, coastal area in Tamil Nadu. Where is Kalpakkam located? Kalpakkam is located in Tamil Nadu. It is also a coastal site, and we have atomic power station also there. We have nuclear reactors and atomic power stations at Kalpakkam. Tamil Nadu has got two nuclear power parks. We have two nuclear parks. One is the Kalpakkam, where we have a research center named IGCR, and the second one is Kudankulam. There is a down south, as we go further south towards Rameswaram side, on the coastal area, before Rameswaram, on the coastal side in Tamil Nadu, we have Kudankulam, right? So there are two nuclear power parks in Tamil Nadu there, right? And two in Maharashtra, as I mentioned, Trombay and Tarapur there. Apart from that, there are other type of scientific centers which conduct research on various areas. One of the very important center for cyclotron and synchrotron, that is a variable energy cyclotron center. There is a variable energy cyclotron center that is in Kolkata. This center is very, very important because scientists and engineers who work with VECC, variable energy cyclotron center, they help in making charged particle accelerator like electron beam to produce high energy electron beam, proton beam, right, particle accelerators, linear accelerators. So VECC comes into that. Even scientists from VECC played very important role in terms of building and maintaining LHC, Large Hadron Collider, which is a charged particle accelerator located in CERN, Geneva, CERN, Geneva, European Center for Nuclear Research, Geneva, right? So in that context, this center becomes very, very important. Not only the VECC, we have other centers as well. Then you know the research center TIFR, Tata Institute of Fundamental Research, that is in Colaba, from where we started our atomic energy research program. It is educational, it is academic and research center TIFR, Tata Institute of Fundamental Research, that is located in Colaba, which is a southernmost point of the Mumbai there, right? There TIFR comes. So there are a lot of such organizations are there. I had given you in the handout location of the research centers on the map of India. Very soon I will be coming to that, but just I have given an idea here. Second, you find here there are public sector, right, utilities, companies are there, PSUs, which are involved in the terms of nuclear power generation and the operation part. They are called operator. What we call that? They are called as operator. They operate the nuclear reactors and the power generation that they operate that, and then the nuclear power is fed into the grid. So here the part of operator, we have two names. One, you are aware, NPCIL, Nuclear Power Corporation of India Limited, that is in Mumbai. It is headquartered in Mumbai. Nuclear Power Corporation of India Limited, NPCIL, that is in. And for India has got 3 stages nuclear power program. Today we are going to discuss 3 stages of nuclear power program. In that context, second stage nuclear power program, we have now created another company, public company, government company called as Bhavini. There is another public sector undertaking or utility, right, undertaking, you can say utility or let's say undertaking, the right word will be undertakings. Government company there, right, PSUs. So there Bhavini stands for Bhartiya Navikiya Vidyut Nigam. Bhartiya Navikiya Vidyut Nigam Limited, that is another company, another government company which has been created for second stage of nuclear power program. Don't worry, I'll come to what is first stage, second stage, third stage, we will discuss in the classroom. But just I'm giving an idea there. So this is the second stage, we have got another company here called Bhavani, right? We have number of other organizations like Atomic Energy Regulatory Board. There are also boards are there, right? Under that we have also a number of boards which work on that. Like first is one is Atomic Energy Regulatory Board, Atomic Energy Regulatory Board, AERB, which looks into the regulation part of it. Then we have got another one, what is called here the Heavy Water Board, heavy water deuterium oxide, which is a very important component of nuclear reactor there. So we have a heavy water board, HWB, which is located in Mumbai. It basically operates the power plant or those kind of plants, manufacturing plants, which generate, manufacture heavy water deuterium oxide. We'll see very soon in the classroom what is the role of heavy water in nuclear power generation. But I'll tell you orally right now that heavy water deuterium oxide, which is based on heavier isotope of hydrogen, deuterium, DTO, deuterium oxide, is used as a moderator in the nuclear reactor. What is the moderator? It slows down the fast neutron. We'll see that, we'll see in the classroom there. We'll be learning about the reactors and all this. So there is a heavy water board, and today India is one of the highest producers, manufacturer of deuterium oxide heavy water in the world. And not only our own requirement, we also supply outside India. We supply to the foreign country also, right? Apart from that, we have a nuclear parks. So if we say there are number of nuclear parks, and today we are having more than 22 nuclear reactors, right, which are operational, and they're working on different nuclear parks in the country, right? So what are they? Like first one, as mentioned here, the BARC center like Trombe and Tarapur. Right? Tarapur, that is both are in Maharashtra. I am writing in a short form there, Maharashtra. Then I mentioned that Kudankulam and Kalpakkam. Both of them are in Tamil Nadu. Then in Rajasthan near Kota in Rajasthan, we have Rawat Bhata. Right, near Kota in Rajasthan, there is Rawat Bhata. Right. Then in Narora, Bulandshahr of UP, there is a Narora Atomic Power Station. That is in Uttar Pradesh, UP. Right. Then Karnataka has got Kaiga, that is in Karnataka. And then in Gujarat there is a Kakrapar, right? Kakrapar in Gujarat. Right? These are the 8 nuclear parks where we have more than 22 such reactors, and we are generating, right, around 7,000 megawatt electricity annually in the country. Nuclear power if we talk about, so nuclear power occupy, right, nuclear power, if you see the percentage, is the 4th position, right, after thermal power plant, right, thermal power generation like coal-fired thermal power plant, thermal station, thermal power. Then wind power, in renewable energy, we have wind power and hydropower in terms of dams and barrages and hydropower there, right? And we are almost like 7,000, nearly 7,000 megawatt, right? 7,000 megawatt generation we are having the nuclear parks. India has a very strong foundation in nuclear science and technology, and with nuclear park and the power generation, we are also expanding the nuclear power for future in terms of using more fuel. Like India has limited uranium, but we have abundant thorium. So what is very important here? The supply of uranium. So India has a limited amount of uranium, right? We have limited uranium, but we have 1/4 of the reserve of thorium in the country, which is found in monazite sands in the coastal beaches or coastal areas of Kerala, Kollam and those areas there. So uranium, but has abundant reserve of thorium, That's why the founding father, Dr. Homi Jahangir Bhabha, right, conceptualized the 3 stages of nuclear power program. About the 3rd stage, the last stage, is based on thorium utilization, right? Worldwide, if you take the reserve, right, around 25% of thorium is found in India, and that thorium is found in monazite sands. That is a type of sands called monazite sand, which contains thorium, right? Monazite sands which contain thorium. So in future, when we go to 3rd stage, when we use the thorium reactor, we will be able to use this abundant supply of thorium, and we can go for power generation for the next 200 years. We have so much of thorium that we can fuel nuclear reactors, thorium based reactors for next 200 years. So we are looking for that, right? And again at the same time, when we talk about nuclear science and technology, it has a dual use, right? It is a dual use technology. You can say it basically comes into dual use technology. What do you mean by dual use technology? The dual use technology means it can be used for peaceful purpose. What are the application for peaceful purposes? The peaceful purposes means here in terms of power generation, atomic energy program, then in terms of nuclear medicine, healthcare, treatment of cancer and all this one. Then agriculture, high yield crops and all, nuclear agriculture, food irradiation, food and agriculture, right? So industry, agriculture, food, water, environment, medicine, healthcare, all we can go for the peaceful use of nuclear technology. But at the same time, you know that military application, nuclear weapons program, where we can have the making of the atom bomb or nuclear weapons, hydrogen bomb, atom bomb, nuclear weapons, that in terms of national security and defense. So again the nuclear technology comes into that. And you all know Hiroshima and Nagasaki, 1945, that Japan was bombed by atom bombs, right? But again, even after 1945, even after the end of the Second World War, right, there are a number of countries which possess nuclear weapons. You all are aware of that, right? So the purpose of using nuclear technology for India is both, that for our atomic energy program, nuclear reactors and nuclear parks, at the same time for agriculture, for medical science, for industry, for environmental aspect, we are using nuclear technology. And then to guard our defense, what is something called deterrence, minimum credible deterrence. You all know the factor of China and Pakistan, right? Our two neighbors. Historically, if you look at the two neighbors, right, the Pakistan and the China factor, and both of these countries, Pakistan and China, possess nuclear weapons. So India has to keep the stockpile of nuclear weapons in terms of geopolitical situation, right? Though, what is the stand of India in terms of having nuclear weapons? The stand of India is that we are having nuclear weapons or stockpiles to provide minimum credible deterrence to our neighbors, right? So that they should not attack India with nuclear weapons in future if such situation arise, right? Conflict or war kind of situation arise, there should not be circumstances where India get attacked by nuclear bombs or nuclear weapons. So we have to maintain that credible deterrence, minimum credible deterrence, right? Again, what is the nuclear doctrine of India? The nuclear doctrine of India says that we have to go for peaceful use of nuclear technology. At the same time, no first use. There is something called no first use policy, right? What do you mean by no first use policy? That India will not attack at any non-nuclear country. What I am using the word? India will not attack any non-nuclear state, right, with nuclear weapons. But there is a information, there is a risk, very high risk and confirmed information that India can be attacked by nuclear weapons. Then in that case, India has a upper hand to use it. But again, India always maintain what? No first use. We will not use the nuclear weapons in the first go, right? And you all are aware Pokhran 1 and Pokhran 2. India has conducted two tests here, Pokhran 1 and Pokhran 2. Now Pokhran 1, right, Pokhran 1 test 1974, right, atom bomb testing was done, underground testing was there. And then Pokhran 2, right, where we also did testing of a small hydrogen bomb that is called thermonuclear weapon. In 1998, we conducted Pokhran 2. And after that, India declared that we will not go for any kind of such underground nuclear test, right? So that's what but India's main use of nuclear technology is for peaceful purposes. Our main aspect is the use for peaceful purpose. So what is the mandate here? If you look at the mandate, right, mandate of the Department of Atomic Energy, the mandate is this one. What is mandate here? The mandate here is that the nuclear technology will be used here. The mandate is that for research and development, R&D, in nuclear science and technology, right? The mandate of Department of Atomic Energy is that to carry on research and development in nuclear science and technology, then develop applications, okay? Applications in nuclear power generation, right? Nuclear power, and we have such reactors in India. We'll see in the classroom what are those reactors. Nuclear power generation, right? Then medical science, healthcare and medical science, like radioisotopes, right? We use radioisotopes. Cobalt 60 is used for treatment of cancer, tumors and cancer. So medical science. Then in terms of industry, right, etc. there, right? That is the mandate we have, okay? But we are also expanding the nuclear power program with the establishment of new nuclear parks, right? We have we have a proposed nuclear parks in future. We are going to have more nuclear reactors and proposed part of it, right? Though there are risks, right? Though there are concerns, issues with respect to the expansion of nuclear technology, but again, we cannot make it zero. We cannot make it a completely zero there. Though there are concerns today worldwide with respect to the nuclear technology application part. As you all know that 3 Miles Island accident in the USA. Then 1986 Chernobyl disaster. Where is Chernobyl? Chernobyl is in Ukraine. Presently there is a country called Ukraine. Earlier it was a part of the Soviet Union. So Chernobyl disaster, nuclear accident. Then very recently 2011 Fukushima in Japan, Daiichi nuclear power plant. Because of earthquake and tsunami, there were explosions of 4 nuclear reactors of Daiichi company, Daiichi nuclear power plants in Fukushima in Japan, right? So again these risks are there, right? There are risks with respect to the use of nuclear technology worldwide. But we cannot in India cannot say that no, now total disarmament, total no use of nuclear technology. We need to expand. But again we have to be, regulate. We need to control that there should not be any kind of leakage of radiation to the outer atmosphere, outer environment, to the water, to the soil, wildlife, environment, human beings, right? They should not get exposed to radiations. You all know gamma rays. Gamma rays are very dangerous, right? This is part of that. So that is what we have to always keep a balance, right? We have to maintain a balance there. Now let's look at here the handout there, the handout which I have given here, and I will just take you to further more organization here. So you can see the handout here, right? Now the handout which will come to your screen, and you'll find in the handout there. The first part is this map is there, right? You have the map part is given there, and I'll just mark you here. See, right from the beginning, Srinagar, Jammu and Kashmir, there we have nuclear research lab, BARC has got, Gulmarg, high altitude research lab which is under the BARC there. Then Narora atomic power station. Now what you see here, we have uranium mines. Let me mark here, right? This one, Mohuldi. Right? Mohuldi, right? Then you have Turamdi, then Bandhu Hurang. These all are the uranium mines. Where they are located? They are located in Jharkhand. Narwa Pahad, we have uranium mines, right? Jaduguda, what is called here? Jaduguda, Bhatin, Narwa Pahad, Bandhu Hurang, Turamdi, Moholdi. All these what you see here, this part, these are the uranium mines. This comes into Chota Nagpur Plateau. Where it comes there? Chota Nagpur Plateau, Jaduguda uranium mines, right? There is a part of the Chota Nagpur, and there is a Chota Nagpur Plateau here, which has uranium, right? And this uranium we are doing the mining there. This plateau in Jharkhand, it is called Singhbhum. What is the name of district here? is the place called Singhbhum. Singhbhum district of Jharkhand, Jaduguda, where we have uranium deposit. And we have a company called UCIL, Uranium Corporation of India Limited, which do the mining of the uranium. Now recently Andhra Pradesh, now I will come to here. Another one here, if you see here, AP, Chittur, Kadapa and Kadapa region there. Andhra Pradesh, Tumalpalle, which I am underlining here, Tumalpalle. We have uranium deposit found in Kadapa. Kadapa, that is a part of the Andhra Pradesh. There is a place called Tumalpalle. Palle means a village. Palli or Palle means village. Tumalpalle. There also we have started the mining of uranium. Earlier where was the Singhbhum district of Jharkhand. But now we have Tumalpalle and we have a companies for that. Uranium Corporation of India Limited, uranium mill and mines there, milling and the mining part. Right. Then you will find here Institute of Physics, National Institute of Science and Education, this part of. Then we have a uranium mine in Bagjata. There is also a uranium mine. All this you will find here. Then coming to here, something very important which I will bring here. If you take the here nuclear reactors and the nuclear parks, I will just change the color here. Now look at here. Where all we have the nuclear power plants, we have in Rajasthan, Rawat Right, we have a nuclear park here. Then you will find here in a part of this one. Narora. This is a part of Narora. Narora Atomic Power Station. Right. This is Narora. Bulandshahr, right, in UP. Then you can see here this one, Tarapur. We have nuclear reactor there. Right. Then Bark, Mumbai. Here the Bark center and all you will find that. Navi Mumbai we have got, right, Navi Mumbai we have the centers, and then we have a Bark also, the Bhabha Atomic Research Center, right. So all this you have there. Then Kakrapar, you can see this is the Kakrapar. Kakrapar in Gujarat, right. Then you can see here, if you go down here, Kalpakkam, right. And then you can see here Kudankulam. This is Kudankulam. These all are the nuclear reactors there, right. Then Kaiga, Karnataka, you find Kaiga. Right. Kaiga you will find here. This is the Kaiga. Right. So Kaiga is there. Then I mentioned that all this one are the nuclear park in the country, and we have so many research centers throughout the country, right. Mount Abu in Rajasthan, we have a Guru Shikhar, this Guru Shikhar, that is a Bark center, that is in terms of astrophysical sciences we have, and we have a telescope by ISRO. ISRO has got a ground telescope in Mount Abu, right. Guru Shikhar you will find. Indore we have Raja Ramanna Center for Technology, right. Then we have a heavy water board. All what you see in the green, we produce the heavy water there, right. So this all green one which you can see here, let's say here, this one heavy water board, right. Then again Talcher in Odisha, heavy water board. Manuguru in Andhra Pradesh, heavy water board is there. The heavy water plant is in Thal in Maharashtra. Then Hajira in Gujarat, heavy water production is there, right. Deuterium oxide is made. So you have this kind of center, you will come across there. India today is a leading producer of heavy water, at the same time radioisotopes also. So through the map I have given you the entire names of the organization institute there. Now UPSC is not going to ask you the names of the institute. This is for your general awareness. UPSC is not going to ask you the name of the center or research establishment or lab or academic center, right. That will not be in UPSC paper there. But as a part of your understanding, when you read current affairs and you come across some name of the research organization, so you know that okay, these are there and this is the main purpose for which that particular research organization has been set up or established, right. Clear there? So this is the first part which I mentioned that, and we are expanding our nuclear park there, right? Now what I'll do here, before I come to the next part of the discussion, there is a question by Tushar Goyal. Tushar Goyal is asking me a question that, isn't it dilemma that developed countries are shutting down their nuclear reactors due to their danger, but India is promoting nuclear reactors for harnessing energy? Very good. Good, Tushar. Very good. Tushar has asked a very good question. Good. Right? Did you understand his question, Tushar's question? Developed countries like France, right, and the other countries like Germany, they have now decided to shut down all their nuclear reactors. And it is here a developing country like India which is expanding the nuclear power program. In future, we are going to have nuclear parks in Haryana, then Madhya Pradesh, we are going to expand in Rajasthan, we are setting up more nuclear reactors, we are planning for Andhra Pradesh to have one nuclear park. Right, Maharashtra will have one more called Jetapur. Jetapur in Maharashtra going to be the biggest nuclear park in the country. And again, very irony is that we are having the collaboration with all these developed countries. Indo-US, Indo-France. We are collaborating with those countries. Now think that. We are having collaboration also, at the same time the developed countries are shutting down their nuclear reactors. And it is here, India is expanding with that. Yes, that is true. Tushar, what you are saying is very correct. But you have to understand why we are doing so. The question is that why we are doing so. I said first reason is the geopolitical situation. What is geopolitical situation for India? The China and Pakistan factor. We cannot shut down our reactors because sometimes from the reactors also we get the plutonium or uranium, and by that we also make nuclear weapons, stockpiles of nuclear arms. Again, the growing need of the electricity. Although India is now going for renewable forms of energy, that is a solar power, wind power, biomass power, we are also looking in future for ocean energy like tidal power, ocean thermal energy conversion. We are expanding our renewable energy program. At the same time, in commitments for clean air, clean environment, reducing pollution, fighting global warming and climate change, right, India's commitment to Paris Agreement, right, we are also going for non-fossil fuel based. So there we are going to reduce thermal power plants, right. Today we have got highest generation of electricity and power in the country from thermal power station, right. But we need to, looking into the future scenario, we have to cut down the such kind of coal is dirty. Coal is dirty. It pollutes the environment, releases greenhouse gases like carbon dioxide. Sulfur dioxide is another type of gas which cause acid rain, nitrous oxide, nitrogen oxide, right. At the same time, one day the coal will be over, right. And another geographical advantage what India has got, that we have got abundant thorium. So we cannot just leave it there, we can utilize thorium for power generation. Though there are concerns with respect to gamma radiation and nuclear waste generation, what I am using the word nuclear waste generation with respect to power plants, nuclear power plants. But nuclear power plant can generate more energy as compared to thermal power plant based on coal. Right? Though there will be pollution, what pollution will be there? Radiation pollution. So we have to work very carefully. We have to look into the future accidents and all these areas. But again, it can generate more. And what is the last point here? Right from the beginning, 1948 onward, after the independence, India has invested heavily, huge investment in the nuclear power program. We have invested so much of money in terms of having Department of Atomic Energy, Atomic Energy Regulatory Board, then in terms of nuclear parks, nuclear reactors. We cannot do away with that. Right? We cannot completely shut down. And at the same time, we have other applications, agriculture, healthcare, industrial application, that also again peaceful use of nuclear technology, right. I had given a handout. So now let's look into the handout here. Now if you see the handout here, I am just going to the next part of the page here. Now look at here. I'll just mark it one by one and then I'll come to the whiteboard here, right. So what is the first point here? The first point is that Atomic Energy Commission, AEC, right. This was set up. When it was set up? It was set up in, I'll change the marker here. Let's say it was set up in, just one second, it was set up in 1948. Just after independence, 1948, right? And made a lot of progress after that. Then Atomic Energy Institute was at Trombay in 1954, it was set up, which was later renamed as Bhabha Atomic Research Center in 1967, BARC. Right? It was renamed as BARC. Right? Then nuclear power projects, as I have discussed in the classroom, Tarapur, Rawat Bhata near Kota in Rajasthan, Kalpakkam, Narora, Kaiga, Kakrapar, right? This is what I mentioned that. And I have given you the map also there, right? You can see the map here. This is the map. These are through the map you can understand how much there is. So India has got total 6780 megawatt, near to 7000 megawatt electricity generation, right? And here you have all the names of the center: Narora, the Rawat Bhata, Kakrapar, Tarapur, Kaiga, then Kalpakkam, Kudankulam, right? We have all of them, and we are expanding also there. Now see here, we have 3-stage nuclear power program. I will be coming to that 3-stage very soon. But now if you see here this one, let me discuss part of it here, this one. Why we need nuclear development in India? I will come to 3-stage program, don't worry. Nuclear reactor and 3 stages, I will be coming to that. But why India need that nuclear power? What Tushar has asked that, the dilemma, where the developed countries are shutting down their reactors, it is India as a developing country is expanding the nuclear power program. And it was asked in the mains exam also there, right? So need for nuclear development in India. What is the first need for that? Right? The first is the energy security. Energy security. What I explained in the classroom, that achieving the nuclear energy security has a potential to provide a large scale of electricity generation. If you compare with coal-fired thermal power station and nuclear power plant will generate more electricity, right, as compared to the coal power plant, coal-based thermal power plant. Right. Then you can see here reduction in carbon emission, greenhouse gases, right, climate friendly technology. It will not generate greenhouse gas, carbon dioxide, which is a major pollutant for the global warming and climate change. India's commitment to Paris Agreement under United Nations Framework Convention on Climate Change, UNFCCC. So nuclear power is reducing global emission of carbon dioxide and sulfur dioxide. Though, what is the problem with nuclear technology? Nuclear waste, hazardous nuclear waste, and the radiation, gamma radiation and all this, right? That is a concern. But it will not going to pollute the air with the greenhouse gases. Nuclear power generation will not generate the greenhouse gases, right? Then you can see a less impact on climate, that does not produce greenhouse gases like coal-based power plant. So, can increase electricity generation without contributing to climate change. Another advantage is what? Replacing conventional energy resources. Conventional sources of energy can be replaced by nuclear power plant. Increase share of nuclear power in the Indian energy mix, right? Diminish the reliance on fossil fuel, replace conventional coal-based energy based. Then continuous supply of electricity. Once we load uranium fuel rod, we can keep on going on continuously till the entire nuclear fuel, that is uranium, is consumed or burnt, right? So here they can provide steady supply of electricity. Like if you compare with renewable energy like solar power, it requires sunlight. During cloudy weather and those kind of situation, the solar panels will not work. Wind power depends on the direction and the availability of wind, speed of the wind. Not every place we can have wind power generation. Wind power mostly happens in coastal area or hilly areas or in desert, right? So if you compare with solar and wind power, nuclear plants are not that kind of dependence on sun or wind, and there will not be any fluctuation. The continuous power supply can be done through nuclear reactors. Then coming to here, nuclear energy and foreign policy nexus, diplomatic relation. Right, we can build foreign relation with USA, Russia, France, that developed country, Australia, Canada. It can help in building the diplomatic ties with advanced developed countries. So that is a nexus can be there. Substantial role in the formation of bilateral relation among countries. Like for example, 2008 Indo-US nuclear agreement. Indo-US nuclear agreement in the year 2008, right, supported India's domestic nuclear plants, strengthening Indo-US bilateral relation, right, giving India the recognition of being a responsible nuclear weapon state. Very important word. Giving a recognition for the country to India as a responsible nuclear weapon state, right, with strong non-proliferation credential. You all know that India has not signed NPT. India has not signed Nuclear Non-Proliferation Treaty. So in that context, it becomes very, very important, right? So challenges here. What are challenges here? Uranium contamination of groundwater due to mining. When we do the mining of the uranium ore, then there may be leaching to the groundwater, and groundwater may get contaminated with the uranium, which is a toxic and hazardous, right? So that can be there, and it has said that groundwater from aquifers of 16 Indian states, Punjab, Andhra Pradesh and all, they have been found the samples of the well in Rajasthan, Gujarat has found the uranium level of more than 30 microgram per liter. That is above the prescribed standard of WHO. Then what you can find here, purity of uranium. For power generation, you require uranium 235, which is very, very less as compared to uranium 238. Uranium 235 is less than uranium 238. So again, the purity part in comparison to world occurrence, uranium deposits established in India are mostly low grade, that less than 0.15% of uranium. What we get from Singhbhum district of Jharkhand, that is a Jaduguda and all this. Then shift towards renewable energy. India is now giving the factor, and we are calling for going towards more towards wind energy, solar energy and all this one, right? Anti-nuclear protests, as you know that after Fukushima disaster in 2011, there have been protests in the country. And one example I can say, Greenpeace Foundation. Greenpeace Foundation has led protest against the nuclear power plant, a nuclear reactor built by Russia in Kudankulam in Tamil Nadu. Tamil Nadu, the Kudankulam, the nuclear power, and there was a setting up of the Russian reactor. So Greenpeace Foundation, an environmental NGO, they led a protest against that power project. You may be aware from the current affairs, right? Jetapur nuclear power plant in Maharashtra, right? Konkan area and the coastal Maharashtra, Jetapur, which is going to be highest there. There has been protest in terms of land acquisition and all this, right? So here you can see that anti-nuclear protest after the Fukushima nuclear disaster in Japan. There have been the protest there, like here, example protest in Mithi Birdi in Gujarat, Jetapur in Maharashtra. Syncing with foreign players. Now again, our nuclear reactor has a very low capacity. Like PHWR, our first stage is with the pressurized heavy water reactor. We use heavy water as moderator and coolant, and it is just a 700 megawatt. If you see here, current manufacturing capability only covers supply of 700 megawatt PHWR with foreign reactors. So what happens in this case? We have to take the help of foreign suppliers, Russia, France, all the private companies. At the same time, we have a limited uranium. Again, we have to depend on them for supply of uranium, low enriched uranium there. So our money, all the, we have to buy for it. We have to buy the reactor, we have to pay them, we have to pay for the uranium supply. These all are the economic concern, right? Apply with the foreign suppliers there. Manpower need. We don't have enough of experts in India dealing with the nuclear technology and nuclear power plants. The scientists and engineers who work were very less, right? So there is to scale up nuclear energy, we require human resource. We require more engineers working with NPCIL, Nuclear Power Corporation of India Limited. We need more scientists working with BARC. So that again will become and we have a shortfall of such a nuclear engineer in India, nuclear scientists in India. Then other issues are there, like problems on land acquisition. Then after land acquisition, there is a problem regarding rehabilitation and resettlement of affected communities, person reserve, forest and tiger sanctuary location, national parks, they can get affected. The socio-political issues are there, public consensus are required. That may also affect the decision making. But when you write mains answer, you have to also bring about that we cannot totally shut down all the reactors and go for no nuclear power generation. We have to keep a balance. So way forward. What comes here? Way forward. So what is way forward? Ensure maintenance of skill base. We require skilled manpower, human resource development. Maintain continue effective safety regulation, very, very important, safety regulation. How do we take care of the nuclear waste generated from nuclear power plants, right? No leakage of the radiation to the environment, right? Then foster progress on facilities for waste disposal and management must be given priority and serious consideration. Nuclear waste disposal and or we have to give the serious part of it. Maintain and reinforce international non-proliferation arrangements there, right? It would be necessary to train and recruit scientists and engineers every year in the R&D units, right? All these are what you can write as a way forward. Mains question, when it comes to mains exam, this is the way you can write there. Why I brought this handout? Just to give you idea how to go about the writing the answer in the main examination. What benefits we get, what challenges we have, and how do we balance it. It has been already asked in UPSC mains exam. If you just go back to the previous year question paper, you will find a question on that. All right. Now what I'll do, now let's come to the part of the whiteboard. See, I've been telling you all the time that whatever I'm writing on the whiteboard, please write it down, right? Additional supplementary material I am doing with the handout. All right. So, I'm now coming to the whiteboard. I hope that you all have copied this whiteboard, because I'll clean the whiteboard and then I'll go to the part of certain more discussion on the whiteboard. It should not happen that the classroom is entire handout, right? We have to supplement handout with the learning on the whiteboard as part of this, right? Any questions so far? Then I'll clean the whiteboard and then I'll come to the other parts of the nuclear technology there. Any doubt, any question you have? Anything you have a question you want to ask there? If you don't have any doubt, then I'll clean the whiteboard. Dear students, you have written that. Shall I clean the whiteboard? Then so that I can discuss other important points with respect to nuclear science and technology. Have you all copied it? Have you all copied it? I'll clean the whiteboard. We'll go to some other topics, right, important topics for nuclear science and technology. Okay, you have done so. Thank you. So let me clean the whiteboard now. Now let's look at certain concepts here. Now I'll come to some fundamental concepts here. Let us first discuss some fundamental concepts there and then we'll return back to the handout there. Right? Now let's look at here. See, when you talk about nuclear reactions, right, when we talk about nuclear reactions, right, broadly we can classify into two types here. The first one is a nuclear fission. and second you come across here nuclear fusion. Right? Nuclear fission and nuclear fusion reaction. Right? You know what happens in nuclear fission? In the nuclear fission, what happens is that heavy right here, the nucleus, nuclear reaction based on the nuclear phenomenon. Heavy nucleus, right here, radioactive nucleus, right, heavy nucleus disintegrate into, right, lighter daughter nuclei. Right? Let's say for example uranium. If we take example uranium. So uranium has got atomic number 92 and mass number is 235, is one isotope is uranium 235. Right? The other isotope called uranium 238. So let's say when a uranium is bombarded with a slow neutron, it captures the slow neutron and it becomes unstable. Right? The nucleus of the uranium 235 captures the neutron, slow neutron, and becomes unstable, and then it disintegrates into barium and krypton and also generates 3 neutrons. Right? And these 3 neutrons are fast. It generates the faster neutron there, which are again slowed down in the nuclear reactor and then used for that. That is the reaction here. Right? Whereas the nuclear fusion reaction, when you talk nuclear fusion reaction is also called thermonuclear reaction. What is called as that? Thermonuclear reaction. Right? It requires very, very high temperature, like the of the order of millions of degrees centigrade, as you find in the star and the sun. Right? Very high temperature is required. So when you talk about nuclear fusion here, so what happens here? Here lighter nuclei, let's say hydrogen, right, combine to form, right, a stable helium, nucleus of helium. Right. So what happens here is that the hydrogen at very high temperature, millions of degrees centigrade, sun and star, it combines to form the another isotope called deuterium. Right? And the deuterium can combine with another deuterium and form the helium. Right? Or there is another part of here that further it can react with the protium, like here where deuterium can react with that, right, and then form the tritium. Right? And the tritium can also react with the protium and can form here the helium. These are called fusion reaction. It requires very high temperature. It doesn't take place at room temperature. It requires very extremely high temperature. Right? Now, if we look at here, nuclear fission reaction can be both uncontrolled and controlled. Right? Let's say, for example, if you take here nuclear fission reaction, we can have controlled and uncontrolled. Right? Like for example, if we take uncontrolled, where we do not control the reaction. So here the application comes in the atom bomb, nuclear weapon. In nuclear weapon or atom bomb, we don't control the reaction, we let the reactions to continue, yielding very high level of energy and destruction which is caused by the nuclear weapon there, atomic weapon or nuclear weapon. Whereas we can have also here controlled kind of reaction here, what is called controlled chain reaction, where we take this fast neutron, again we slow down the neutron, captured by other uranium nuclei and again disintegration. and we can control the amount of energy here generation, and then we can use for nuclear power generation, atomic energy program. So here control chain reaction, and for the control chain reaction, what we use? We use here nuclear reactor. In the nuclear power station, nuclear reactors are used for power generation. Atomic energy program there. Nuclear power generation. Right? Now, fusion reaction. Fusion reaction can also be divided into two forms. Generally, it happens, nuclear fusion reaction generally happens in the uncontrolled manner. Where it is an uncontrolled manner? If we talk about uncontrolled fusion reaction, what is fusion reaction? Thermonuclear reaction. So where do you come across? You come across example of stars. Galaxies has got billions of stars. Stars, the source of energy is nuclear fusion. Then our own sun, which is star of the solar system. Again, the source of energy is nuclear fusion. Then if we have to use an uncontrolled manner on the earth, so we can have a thermonuclear weapon, what is called hydrogen bomb. Hydrogen bomb, thermonuclear weapon. What happens in hydrogen bomb? Initially we carry out fission. What we have the first stage? Fission, which generates energy, heat. It generates heat energy. And when the heat energy is very high, when the temperature goes higher, then hydrogen and hydrogen fuse together, and then it generates tremendous amount of heat and the energy. Hydrogen bomb is more lethal than atom bomb. India too has got thermonuclear weapon like hydrogen bomb, and we have done a small thermonuclear testing in Pokhran 2 in 1998. Right? But US, China, Russia, other countries, they also have. Now what comes here, next one, I am writing here. Now comes the question, can we control fusion reaction? It's a very important question. Can we control a fusion set of reaction? Yes, we can control that. It is also possible to control fusion reaction, and we can use certain type of reactors. Now what is the name of the reactor here? There is one type of reactor called as a tokamak reactor. What is called as tokamak? Tokamak reactor. What is tokamak reactor? Tokamak reactor is a toroid, donut you have seen the donut or toroidal type of a reactor, right? Toroidal type of a reactor called tokamak reactor. Within the tokamak reactor we can confine plasma. What is plasma? Ionized state, very, very high temperature. We can confine the plasma, very high temperature plasma, within a kind of a vessel, within a kind of reactor, which is called tokamak reactor. Recently China has developed artificial sun. What makes the headline? Artificial sun. The artificial sun, right, built by China, has achieved highest temperature on the earth using this kind of a superconducting kind of a tokamak reactor with magnetic induction. It is generated with that kind of temperature. Now question comes, can we go for power generation? As we are using here uranium based controlled chain reaction in nuclear reactors to produce electricity, is it possible to use the thermonuclear reaction, fusion reaction in a controlled manner and then go for power generation? Yes. Yes, it is possible. Now a very ambitious project is going on, that is called ITER, ITER. What is the name of the project? ITER, International Thermonuclear Experimental Reactor. China, India, Russia, USA, Japan, South Korea, France, other European countries, they all are partners into a very important project that is taking place in France, south of France. There is a place called Cadarache, and India is also partner in that project, where commercial power generation using hydrogen, a tokamak reactor is being now built on that, right? That is now being built into that. So yes, that is also possible here. With respect to here, what I am now writing here, there is a project called ITER, International Thermonuclear Experimental Reactor. International Thermonuclear Experimental Reactor. I had given you in the handout also there, but I'm just writing the point on the whiteboard so that whenever you read your classroom, you will be aware of the ITER. Where is located? This project is now in a place called Cadarache. Cadarache in south of France, southern France. This is being built up. International Thermonuclear Experimental Reactor, ITER, right? Now in this one, it is basically here a large tokamak reactor here, right? Magnetic induction based, there is high temperature. Here, high temperature confined, right, plasma generated using magnetic induction. What is magnetic induction? As you change the magnetic flux, magnetic field, it will generate current. Faraday law. There is a law called Faraday's law. And that current can have a heating effect, which can generate high temperature. So, it is basically high temperature confined plasma generated using magnetic induction in a controlled manner, within a tokamak reactor. India is a partner in the project within tokamak reactor using hydrogen. It will use hydrogen as a, you can say, as a fuel, right? And whatever heat is generated, that will be absorbed. Water will convert into steam. What the nuclear reactor does here, even the normal fission reaction of using uranium and thorium, it absorbs the heat and then heat converts water into steam, and that steam moves the turbine generator, which produces electricity, right? So here, so what is this ITER project? Is high temperature confined plasma generated using magnetic induction in a controlled manner within a tokamak reactor using hydrogen. Hydrogen will be used there, right? And this will be used for power generation. Now imagine that if this is become possible, right? Using fusion reaction, it will solve a lot of problem of energy worldwide. When we use uranium in such kind of fission based reactor, it generates radioactive nuclear waste. But if you use the hydrogen as a fuel, what is the end product of hydrogen? Helium. So such kind of power generation in a controlled manner will not generate radioactive nuclear waste. And again, helium is very precious. Helium has a lot of demand in the industry. It's a light gas, hot air balloons and all, they use helium. So same helium which will produce in this kind of a tokamak reactor in the ITER project can be used for industrial application. Hydrogen is abundant. What is the fuel here? Hydrogen. Hydrogen is abundant in the universe. So mankind can keep on going on hundreds and thousands of years continuously, can use this kind of technology for power generation. One day uranium will be over. One day plutonium, thorium, uranium, all will be exhausted from earth crust. But hydrogen is going to be forever. There will always be hydrogen. So this is going to be future of power generation, right? Now another in this context, there is another development. China has done that. Our neighboring country has done artificial sun. It has gone for artificial sun. Right? China has done that, has achieved such a high temperature. Like artificial sun, China has done that. So again, it has a tokamak reactor. Here, superconducting process based on a high temperature tokamak reactor, that is HL2M, that is the reactor which produced highest temperature. Now question comes that, do we have tokamak reactor in India? Do we have any tokamak reactor in India? Yes, we do have tokamak reactor in India called as Aditya. There is in Gandhinagar in Gujarat, there is a Institute of Plasma Research, Institute for Plasma Research, IPR. It comes under Department of Atomic Energy. This is located in Gandhinagar in Gujarat. We have from 1980s onward Aditya tokamak reactor. India too has got a tokamak reactor for plasma research. And what is the name of this reactor? We have given the name Aditya tokamak reactor. It is right from the 1980s. Right from 1980s, India is using Aditya tokamak reactor, which is located in Institute of Plasma Research, that is in Gandhinagar in Gujarat, under Department of Atomic Energy. It is not that India doesn't have such kind of reactor. It is not that India doesn't have the technology. We too have the technology. Right? And we are using from 80s onward the Aditya tokamak reactor. One Aditya we have discussed in space science and technology, Aditya L1, that is solar mission of the ISRO. Now I am introducing another Aditya. What is another Aditya? It comes in the context of fusion, nuclear fusion, plasma based thermonuclear type of vessel called tokamak reactor, which is located in Gujarat. So you should know in what context the name comes, the name of the technology comes. Right? Clear there? Now let's go to the handout. That's what I said, that I will use the whiteboard and handout, right, to make you things clear, make you everything clear there. So now let's come to the handout. Now let's look at the handout. One by one I will be going through all such areas there, right. Now if you see the handout here, इनको handout दिखा दीजिए. Now let's look at after the handout here, in the part you have here ITR, International Thermonuclear Experimental Reactor. You can see here ITR is there, International Thermonuclear Experimental Reactor you have. So now please refer to the handout now. I have given detailed part of it. If you see here ITR, right, International Thermonuclear Experimental Reactor, right. Now see here, what is comes here? This ITER, right. It is important for the UPSC examination. Now why it was in the news? India has recently completed 50% of the work assigned to it under the ITER project. India being a partner has completed 50% of the work. Now you can look at here, very important, in the bracket, in this box you have on the tokamak. That's what I said, whatever I am teaching in the classroom, whatever I am discussing in the classroom, I am supplementing that information in the handout. And this can be important. I'll mark here, this is important for the examination. UPSC can ask you question on that. Right? Now let's see what is given here. The tokamak is an experimental magnetic fusion device, right, to harness energy of fusion. Inside the tokamak, energy produced through the fusion is absorbed as heat in the walls of the vessel. Whatever the heat energy generated in the wall of the vessel, it absorbs that, right, which will transfer the heat, this one, which will be used by a fusion power plant to produce steam, and then that steam will move the turbine generator to produce electricity, right. Now the device uses magnetic fields, magnetic induction, Faraday law, F-A-R-A-D-A-Y, Faraday's law is there, to contain and control hot plasma. What comes here? Hot plasma, just like sun and the star, right. Hot plasma, deuterium, tritium nuclei to produce great amounts of energy. What is plasma? Plasma is an ionized state of matter similar to a gas, right. A gas becomes plasma at extreme temperatures, very high temperatures. The machine, the tokamak reactor, is designed to produce 500 megawatt of fusion power. ITER project will generate 500 megawatt of electricity using fusion power. Then demonstrate integrated operation of technology for a fusion power plant, such as heating, control, diagnostics, cryogenic, remote maintenance. Then achieve a deuterium tritium plasma in which the reaction is sustained for a long duration through internal heating. Test tritium breeding, since the world supply of tritium is not sufficient to cover the needs of future power plants. It will generate tritium, that is the heaviest isotope of hydrogen. Hydrogen exists in 3 isotopes: protium, deuterium and tritium, right. Now demonstrate the safety characteristics of fusion device. It has to be a safety one. We have to always take into consideration safety. So such as the control of the plasma, fusion reaction with negligible consequence of to the environment, right. Now if you see here about ITER project, right, about the ITER project here. So what is about ITER project here? About the ITER project, it was launched in 1985. When the project started? 1985, and is an experimental fusion reactor facility currently under construction. It has not been operationalized, it is under construction. Where? Cadarache, south of France. I have underlined the words there. Sometimes the question, there can be the information or the facts can be asked. Now look at there. There is a feasibility of nuclear fusion as a future source of energy and build the world's largest tokamak through an international collaboration. Then once completed, ITER will generate fusion power there. Who are the member countries of ITER? The signatories include China, European Union, India, Japan, Korea, Russia and US. 35 countries are the member parties. Now these countries share the cost of project construction. They share the cost of project operation, construction, decommissioning, right. Will also share in the experimental results and any intellectual property generated by the project, right. European Union, EU, that contribute 45%, while the rest, right, each of the party contribute 9%. India is giving 9% of the total fund there, right. So 9/10, around 9/10 is being given by procurement is for the ITR components. Each member has a domestic agency to fill the need. India has got DAE, Department of Atomic Energy, as a domestic agency to deal with this project, right. Now India has formally signed, joined the project in 2005. When India became a member there, India joined in 2005, right, and is responsible the delivery. What is responsibility of India? Delivery of cryostat, in-wall shielding, cooling water system, cryogenic system, heating system, diagnostic neutral beam system, power supply, some diagnostic. Not very important for the exam, but just the point is there. I am just giving you that point here. This all equipments will be supplied by India, right, and India has contributed resources about $2.2 billion in this effort. ITER India is the Indian domestic agency. What is the name of the domestic agency? ITER India, a specially empowered project by the Institute for Plasma Research, Gandhinagar, which comes under Department of Atomic Energy, where we have Aditya tokamak reactor also. And then you have a difference between the nuclear fusion. All are there in the handout. You don't have to worry about it, right. You can see here splitting of heavy nucleus, right. This is what reaction you have. Lighter nuclei form. Here fusion of 2 light nuclei to form the helium. The reaction is there. I have already given you flow chart on the whiteboard. Then uranium, plutonium are used. Here atoms of tritium and deuterium are used, isotopes of hydrogen. Energy produced is lesser than the nuclear fusion. Fusion will have several times greater the energy than the fission. Hydrogen based fusion will generate much higher energy than uranium and plutonium or thorium based fission reaction. Now fission reaction produce highly radioactive nuclear waste, but fusion will produce no such radioactive waste. It will generate the inert gas helium, which can be further utilized for industrial application. Additional neutrons released in the fission reaction can produce chain reaction sustained for a longer duration, right. But here tremendous amount of pressure and temperature needed to join the nuclei together. That's what you require, very, very high temperature. That is one of the challenge of ITER project and such kind of a plasma based fusion devices, to maintain such high temperature, generating such high temperature. Right, that is challenging part. And advantages. Now you can have advantages here. What is advantage here? What are advantages of fusion power? Abundant energy. Hydrogen is abundant. If it can controlled way release nearly 4 million times more energy than a chemical reaction by burning of coal and gas, and 4 times more than the fission reaction. Sustainability, another thing, sustainability. Widely available hydrogen is widely available. We can keep on using forever. Zero carbon emission. From fusion, what will form? Helium. And helium is not a greenhouse gas. Helium is not a greenhouse gas, right? Then no high activity, long lived nuclear waste. It will not generate long lived nuclear waste there. Uranium and plutonium based nuclear power plants generate high amount of and long lived nuclear waste generation. Limited risk of proliferation, like uranium based, plutonium based graded nuclear weapons, atom bombs can be made. But here there is no risk of that. Fusion doesn't employ fissile material like uranium, plutonium. No enriched materials are required in this case. No risk of meltdown in a tokamak device there. But that can be a challenge there. How do you maintain the temperature? If the temperature goes beyond the control, then it can be a big problem for power generation using a tokamak reactor, right? So here, maintain the precise condition necessary for fusion. Cost, the average cost per kilowatt of electricity will be lower there. See, I am talking about average cost of generation of electricity, 1 kilowatt hour of electricity using fusion, the average cost, and compare with the uranium plutonium based, that may be lower. But again, tokamak reactor and such kind of technology of fusion power is a very expensive project, right? We have to take into account the both positive and negative aspect. Both positive and negative aspect you have to take into account. And issues are there with issues related in the box. You have issues related to India's participation in ITER, delay in cash contribution since 2017. India has not fulfilled that one. Low allocation of human resource on the ITER site. Only 25 Indians are currently working on the site. It requires 100 engineers and scientists there, right? India has deputed a junior person to represent the country, right? Again, we require more experts there, right? Then you can see here this one, conclusion. So by the end of the century, demand for energy will be tripled because of growing population, urbanization, and the more need of electricity in developing countries. It will become tripled, 3 times more. So this future technology can be used, right? So relying on fossil fuel alone cannot help in energy production, both in practical way and so access is required to resources, right? Not to cause damage to the environment, reduce global warming and climate change problem, right? So fusion power is the future power generation, right? So I have discussed the part of this handout except one topic, that is 3 stages of nuclear power generation, right? 3 stages of nuclear power generation by India. We will go into that. Now any doubt you have, I'll come to the whiteboard. That's what I am using, whiteboard, and then I am marking the points in the handout, right? So that you are able to connect both of them together. Any doubt, right? Any doubt you have with respect to what I have discussed with the ITER project and all this one, fission and fusion. We will now see the India's 3-stage nuclear power program. I am going to discuss that one. But you have anything to ask with respect to what I have just explained about the ITER projects and all this one? Tokamak reactor and all this. And China has developed artificial sun, right? Recently, China has built artificial sun, higher temperature there. If you see here, let me show you there. If you just do the Google search here, I'll take you to the Google search here, this one. It has made all headlines there. Artificial sun, right, China. If you do the Google search, artificial sun, China, this one you have. Right, you have all the coverage in the article. China turns on nuclear powered artificial sun. China successfully powered up its artificial sun nuclear fusion, right, reactor for the first time, right? And the name of the reactor is this one, HL2M tokamak reactor. What is the name of the reactor? HL2M tokamak reactor in China. that is the largest and most advanced nuclear fusion experimental reactor, right. Then you can see here, it uses powerful magnetic field to fuse hot plasma and it can reach up to 150 million degrees Celsius. 150 million degrees Celsius, right, 10 times hotter than the core of the sun. It was achieved in the lab. Where it was done? Southwestern Sichuan province of China. Southwestern Sichuan province of China. This is called artificial sun, right. So you'll find in the news, you'll find all this in the news there. Then you can see here, right. China turns on artificial sun, Hindu, the Hindu newspaper, right. This one you can see here, this is the reactor. You can see this is the reactor here. Right, this has been built now, and Hindu paper has come out with this artificial sun, HL2M tokamak reactor. Now this can be asked in UPSC exam, right? It can come in the UPSC exam. Same 150 million degrees Celsius there, right? Now there are a few doubts there. Let me address the doubt here. Rahul is asking a question there. Let me go near to the screen and read the question first. Then I'll give you the reply of the question. Rahul is asking this question. Please explain India's role in ITER and why India joined so late into it. I've already explained, Rahul. India's role in ITER is that whatever the equipment, now only I have marked in the handout, no? Just refer to the handout. What is the role of India in the ITER? That India is contributing in terms of providing the equipment, cryostat, all those kind of instruments which India is now providing that. At the same time, the engineers and the scientists who are working on the site in the ITER project. And why we are doing so? We are doing so because when this ITER will be successfully implemented in terms of generation of power, the same technology will be, IPR will be shared by India, and India will use the same technology, will transfer that technology, and we will build such kind of a commercial based fusion power reactor in the country. Imagine that in future, maybe down the line 10 years or 15 years, same technology based fusion reactor we will build in India, and we can go for the power generation. That will save our money. Whatever money we are investing right now with the ITER project, we are going to save a lot of money when such technology will be fully developed, and we will contribute in the country there, using the country there. Now you are asking another question, why India joined so late? Because initially we were not prepared to be part of such kind of global project, a mega science project. You can call this as a mega science project, right? 85 it was started, then slowly the one reason may be European country, France. They would not have allowed the other countries to, initially when the project started in 1980s and 85, it was only intention that only European countries to carry forward that particular project. But then later on, they would have opened for other member countries to join, like US, China, Japan, Russia. So India got the opportunity to join there. Where the project is being conducted, that is in European countries, south of France, Cadarache. So initially it was all European country oriented project, solely by European country. Then later on it went on to other countries, right? At the same time, we have to see that government decision, DAE, which department will come into this particular project? Department of Atomic Energy. And Department of Atomic Energy comes under where? PMO, Prime Minister Office. So you can say the previous government, there may be delay in the approval of the project, or in terms of considering all the decision to go for India joining the project, that can be a factor, right? So now another question, Arjit is asking question. A basic doubt always come to him, that how come hydrogen is a different element altogether in periodic table, and then how it becomes a helium which is also another element possible there. You would have studied in basic science. You don't have to mug up. There is no need to mug up. If you have read in the basic science class, there is a process called transmutation. What is the process called as a transmutation? What is transmutation? Where the nucleus of an atom, right, transmutate, convert into another nuclei of different atom. Now what happens in this case? Let's understand that. What happens there? Chemical property of an atom depends on electrons. Since you would have covered in your basic science class, but then Arjit is asking question, I am explaining that. The chemical properties of any element, right, whether you talk about hydrogen or helium or carbon or nitrogen or any kind of metals, sodium, potassium, whatever you take there, that depends on the electrons which participate in the chemical reaction, bonding and all this one. Electrons are found outside the nucleus of an atom, whereas the nucleus of an atom is made up of protons and neutrons, what is called nucleons, right. That is called as a nucleons there, right. That is only determined the physical form, the physical factor, the physical weight and all this comes into that, right. Now what happens is that if we bombard with the neutrons, nucleus, I am talking about nucleus of that particular atom, if we bombard it, so what will happen? If the nucleus, the number of protons changes, if you are able to bring about change in the proton, because in the nucleus the proton and neutron, there again is not a very static, it is very complex ongoing kind of changes. There is always conversion happens there, and if that converts into one more proton or reduce in the proton and changes there, which can lead to the changes in the electronic configuration, can give rise to a new element. In the periodic table, you will come across, if there is any loss, let us say unstable nucleus which undergoes radioactivity, if it releases alpha particle is made up of helium. So there, what is alpha helium made up of? 2 as atomic number, 4 as the mass number. What is atomic number? That is number of electrons, that is equal to number of protons. And what is mass number? That is total number of nucleons in the nucleus. That is the total number of neutrons and protons. So helium has got 2 electrons, 2 protons and 2 neutrons. So alpha particle is a helium nuclei, helium particle. So when there is release unstable nucleus, heavy nucleus disintegrate when there is radioactivity and disintegrate, breaks and releases alpha particle, which is helium nucleus. So what happens that there will be change of 2 atomic number, 2 and 4 mass number. So that element will get transmuted, right, into an element which will be 2 places left in the periodic table, right. That is what happens there. Whereas a beta particle, when there is another beta rays, what is beta particle? Beta particle is fast electron. If there is release of fast electron from the nucleus of an atom, where the atom nucleus contains proton and proton breaks into electron and the part of something, then the electron which releases, so there will be change again with the atomic number, and that will be right side of the one place, right. Whereas gamma rays, when you talk about gamma rays, gamma radiation is a form of electromagnetic wave, EM wave, which is a form of energy, and that comes from Albert Einstein's equation, that is called mc square, delta m, that is a mass defect, into c square. C square is the speed of light, square of the speed of light. So when an atom changes from one nucleus to the another one, there is some change in the mass, and that is called mass defect, and that mass has got converted into energy, that is by Einstein, delta m c square, and that energy is in the form of gamma rays, gamma radiation. Gamma rays always accompany with the alpha and beta particles. This is your chemistry class. I am very sure, I don't know whether in your basic science class, your chemistry or physics class, you would have covered this one. Is it clear, Arjit? I am not writing on the whiteboard. Please go back and review your basic science class if it is covered, or read NCERT textbook. You will get this understanding. Transmutation part, right? What is the word there? Transmutation. Now Pawan is asking another question, what kind of metals can resist without melting those high temperature? Very good question. There are many, this is very good question, because the nuclear reactor, you have to build with such kind of metals and all, or such that it should not get melt down. Zirconium, I'll give you one name, zirconium, ZIRCONIUM, right? Silicate, even silica also is a high, like silicate, silica based tiles and all, they can also resist very high temperature. Zirconium or zirconium based alloys, they can tolerate very high temperature, right? They can tolerate very high temperature. Zirconium, ZIRCO, and based on alloys, they can tolerate very high temperature. Is it clear, Pawan? What you asked the question there? All right. So what I'll do now is that we will go into another very important concept. I'm coming to the whiteboard. That is a nuclear reactor technology. Let us now discuss about nuclear reactor technology, and we will discuss about 3 stages of nuclear power generation of India, right? So first, have you all copied this whiteboard? Tungsten can also be there. Yes, tungsten can also there, but we don't use tungsten in the nuclear reactor. We don't use in tungsten nuclear reactor. We generally use the zirconium and alloys of zirconium and all for that part. But yes, tungsten can also tolerate high temperature. Acha, Mansi is asking for a break. Do you want a break here, or shall I continue with the class? Okay, Neha is also asking for a break. All right, so let's have a small break. Let's have a small break. After the break, I will discuss about these 2 important area, nuclear reactors and nuclear reactor technology. Let's have a small break. Okay, thank you. Let's have a break here. Okay, we will resume back. I said that I will be now teaching you the nuclear reactor technology. So let us go into that. And we'll connect this one with India's development of 3 stages of nuclear power program. So nuclear reactor, if we look at a nuclear reactor, let me just draw a rough diagram. See, a nuclear reactor, you will find that it is you have a core of the reactor, right, which is heavy walls are given so that the radiation should not leak out to the environment, and at the center you have the core. I'm just drawing a rough sketch of that, where the nuclear fuel bundles, the fuel rods are kept there. They are hundreds and 200, that depends on the power generation capacity of the reactor. They are kept in this fuel bundle assembly. There is a fuel bundle assembly there, right? And there it is kept. These are the fuel rods, which I am drawing on the diagram there, right? They are kept at the core of the reactor, and this fuel rod will be made of uranium, plutonium. So we'll be seeing that what type of fuel can be used there. So there, this is at the core of the reactor you have, right? Now what you have a controller rod. You'll find here the controller rod. The controller rods go inside the reactor, right? It is inserted inside and outside. You have the controller rod. Plus, you will also have here the supply for moderator. You have a supply for the moderator, right? So let's say here I am drawing here. There's a where you have a primary cycle. There's one cycle which supply the moderator. Which passes through the reactor. And whatever the heat is generated because of nuclear reaction, so that heat will be carried by the there are different designs are there. See, what is main aspect? The water which is pumped inside, it will absorb the heat and will form the steam, right? What the water goes inside here, the steam goes. Now the steam that is fed into generator, steam turbine generator. And this turbine generator will produce electricity, right? And again the steam is condensed, right? The steam is condensed, this condenser will be there, which will condense back the steam into water and again pump inside. Right? Here you have a steam generation. Here the water which goes inside will absorb the heat, will convert into steam, will go to the steam chamber, steam will pass into the turbine generator which will produce electricity, and then steam is condensed back into liquid water and pumped inside. Right? This is the moderator. So what is the role of the water? Water has got two roles here. One is the coolant, keeping the temperature of the core at constant and absorbing the additional heat that is done by coolant. Sometimes we can also use heavy water, right? We can also use heavy water as both coolant and moderator. It can cool also and moderate also there. Superheated deuterium oxide or heavy water. That is in a reactor called pressurized heavy water reactor. We'll see that one. I'm just drawing a normal diagram. See here, now I'm just giving a normal diagram of the reactor. Though there are different types of reactors we'll see in the classroom, but just a normal understanding here. And this is here where you have the moderator. Then you have here controller rods. And then you have here the core of this is the core of the reactor. And here you have a fuel rod. All these fuel rods are there. Here this is the fuel rod, bundles of fuel rod. Right. This is just a rough sketch. I've just drawn a rough sketch of a nuclear reactor. Though there are different type of design, the different type of designs of the reactor. We'll see here. We'll see in the classroom. Now what are they here? There are four important components. Let's understand here four important components of a nuclear reactor, which I have just sketched on the whiteboard. Right? Which are those four important components of a nuclear reactor? The first is the fuel. The radioactive fuel is there. So the first component what comes here, that is the fuel. Fission reaction, right? So fuel here, that is in terms of fuel, is the bundles of fuel rods, right? Bundles of fuel rods, right? As a fuel rod assembly is kept there. Now what we can use is the fuel. Fuel can be uranium, natural uranium, or even can be plutonium, or even we can use thorium. Whichever may be that, natural uranium or plutonium or thorium, we can use that. That depends on what type of reactor is there, right? So this is here, produces heat energy by controlled chain reaction, controlled nuclear fission chain reaction by absorbing neutron or whatever the process are there. Now second component of a nuclear reactor is the moderator. Right? Now moderator can be here. What we use here? Here we use heavy water. That is a deuterium oxide. Right? Now what is the moderator does? It slows down fast neutron which is produced in the reaction here. It slows down the fast neutrons. Right? Thermal neutron, there is something called thermal neutrons. Right? Which can be captured by uranium nucleus or nuclei. The main role of a moderator like heavy water is to slow down the neutrons so that it can be captured by uranium nuclei to undergo fission reaction. Right? To slow down the fast neutrons which are produced in the reaction. Uranium when split produces the faster neutron which will be slowed down. The thermal neutrons will be slowed down here. Now third component here is the coolant material. Right? What is coolant material? It keeps the temperature here to cool the core of the reactor. Right? Maintain constant temperature so that it should not get overheated. Constant temperature. Absorb. How it will do that? Absorb excess heat. Whatever excess heat is produced, absorb excess heat energy. Now understand, if the reactor is a BWR, boiling water reactor, if the reactor is a boiling water reactor, what will happen? The water which is going inside the core will absorb and become steam. Direct conversion of steam. And the steam will go outside the core of the reactor and pass through the turbine generator, steam turbine, and then generate electricity. But if it is a PWR, pressurized water reactor, so what we do in pressurized water reactor, we don't convert water directly into steam. Understand this is very, very important point I am talking about. If you have a boiling water reactor, direct, very first generation, older technology, the water which is fed as a coolant, when it goes to the core, will absorb the heat, convert into steam generation inside the core. And that steam will go to the outside to the turbine generator where it moves mechanical to electrical and then produce electricity, and then steam will be again condensed back and recirculated. A single cycle is used. But there is another type of reactor called PWR, pressurized water reactor. What happens in pressurized water reactor? Either we use normal water or we use heavy water. Heavy water is both as a coolant and moderator. What is the main role of heavy water? Moderator, slow down the neutron. But we can use heavy water along with moderation, along with moderator, also as a coolant material. Now what happens in PWR, pressurized water reactor? The water which goes inside the reactor core is sent with high pressure, is pressurized. Now, very important concept which I am now telling you here is that boiling point of water depends on pressure. Right? Boiling point of water depends on pressure. If pressure increases, boiling point will also increase. And let's say when you feed the water into the core of the reactor with very high pressure, water will not boil at 100 degrees centigrade. Generally you know that normal atmospheric pressure, water boils into steam, right, at 100 degrees Celsius. But let's say if you have a high pressure, very high pressure, when you apply very high pressure, pressurized it. So what will happen there? the boiling point of water will increase 300 degrees centigrade, let's say 300 degrees centigrade, 300 degrees Celsius. So what will happen in this case? The water will remain as a super hot water, right, without converting into steam. And that superheated water can go outside the core into another chamber where it will transfer this excess heat of the superheated water to another cycle where you have a normal water, and that normal water absorbs the heat and becomes steam at 100 degrees centigrade. That is called PWR. Now in PWR, if you use heavy water, it is called PHWR, pressurized heavy water reactor, where what we do, heavy water deuterium oxide is used both as a moderator and coolant. It will cool the reactor core, absorb the heat, but it is passed under pressure, pressurized. So the boiling point becomes higher, 240 degrees Celsius, 250 degrees Celsius, 300 degrees Celsius. So it will become superheated heavy water, will absorb all heat and go superheated outside there. And then you have another chamber where normal water, light water, normal ordinary water will take the heat from the pressurized superheated heavy water and then convert into steam, normal water, and that will feed the turbine generator to produce electricity. That is another design. So what I want to make you understand is that pressurized water reactor is that type of reactor where we use a single component, that is a heavy water, both as a coolant and moderator. It cool the reactor also, moderate the reactor also. See what I have done here, this diagram is a boiling water reactor. This diagram is a boiling water reactor. It has a separate moderator, it has a separate coolant. And here what happened, the water which goes inside absorbs the heat, becomes steam, and that goes outside. So this is the design of a BWR, boiling water reactor. But in the pressurized water reactor, we don't use a coolant and moderator separately. We use a single cycle, where heavy water will do moderation. What is moderation? Slowing down the neutron. At the same time will absorb heat, become superheated, and that will pass to the next chamber where you have ordinary water which will absorb the heat, become steam, and then make the turbine run. Right? That is a basic difference. So what I want to make you understand, the coolant, the role of coolant is that to cool the core of the reactor, maintain constant temperature, absorb excess heat energy, right, from the core. Right? And we can use coolant. What we can use called coolant? We can use light water, normal light water from river or ocean, or we can also use heavy water as a coolant. There are some type of reactors which may not use the normal water, ordinary water, light water or heavy water, can also use liquid sodium. I'll give you one example of a liquid sodium cooled reactor. Breeder reactors, like in India, we have developed FBRT, fast breeder reactor technology. Now fast breeder reactor, second stage of India's nuclear power program is in Kalpakkam, and there as a coolant we use liquid sodium. I'll be telling you with the diagram there, don't worry, I'll make you understand through a diagram. It uses the liquid sodium as a coolant, but normally we can use the normal water or heavy water. Now what happens in boiling water? In boiling water reactor, BWR, right, normal water, right, as coolant, right, converts into steam. In the core of the reactor. What I have explained with the orally I am writing here. What happens in boiling water reactor? Normal water as coolant converts into steam in the core of the reactor, and that comes out. This is the reaction of BWR. This is schizodiagram. Now I'll tell you what happens in PSWR. Whereas in PWR, right, in pressurized heavy water reactor, PHWR, right, heavy water, deuterium oxide, heavy water is passed under pressure to become superheated. Water which transfer heat. There will be heat exchanger will be there. Transfer heat to another chamber. Transfer heat to another chamber where normal water absorb heat and become steam. Let me read out there. As a coolant, what I have said here, see, in coolant, what is the role of coolant? To cool down the core of the reactor / maintain constant temperature / absorb excess heat from the core. Now in BWR, boiling water reactor, arrow, normal water as coolant converts into steam in the core of the reactor, which go to the steam turbine and produce electricity. Whereas in PHWR, like here, pressurized heavy water reactor, deuterium oxide heavy water is passed under pressure, to become superheated hot water. Water temperature goes to 300 degrees centigrade or 300 degrees Celsius, which transfer heat to another chamber. There will be another chamber outside. That another chamber where normal water absorb heat and become steam. Now what happens in the case of PSWR, pressurized heavy water reactor? You have a single circulating pipe which will pass the heavy water inside the core. It will do the cooling also, moderation also. And that hot water, superheated heavy water, will get transferred to another chamber which will have the normal water. So what happens in PSWR? You have one where you have a core of the reactor and you have another as a steam generation. Now in the PSWR, in one core here, we use one circulating pipe which will carry heavy water both as a coolant and moderator. Now the superheated hot water, the heavy water passing through the core, which will do the moderation, slowing down the neutron, and at the same time will absorb the heat as a coolant, will remain as a superheated heavy water. And there is another chamber, the second chamber, which where the superheated water 300 degrees Celsius will transfer the heat to the normal water in the second chamber with the normal water and that will absorb the heat, right? Steam generation, absorb the heat and 100 degrees centigrade boil into steam, and that will go to the turbine generator. Clear? So that's the another one. And where we use a liquid sodium, fast breeder reactor, FBR. In FBR we use liquid sodium. So in FBR, fast breeder reactor, let me write here. In FBR, fast breeder reactor, liquid sodium is used as coolant. Now what is the fourth component? The fourth component is the controller rod. Now controller rods are made up of boron, cadmium. We use boron or cadmium as a controller rods. Now what controller rod does? What is the role of controller rod? It absorb. I am using a very important word, absorption. Absorb excess neutrons to control the reaction, to control the chain reaction. The role of controller rod is to absorb neutrons, because the reaction will keep on happening inside the core. It will keep on generating more and more number of neutrons. So what the boron or cadmium based controller rod does, it absorbs neutrons. Right? And that absorb neutrons, so that the neutrons number can be controlled inside the core. If you are able to control the number of neutrons, you are able to control the number of reactions. And if you are able to control the number of reactions, you are able to control the amount of heat generation. Very important statement I have made. If you are able to control the number of neutrons, whatever available neutrons, that will be the number of reactions. And whatever number of reactions, that will produce that amount of heat. Right? If we have to shut down the reactor, close the reactor. So what is the point here in this case? That controller rods will absorb all neutrons. When there is no neutron, no reaction. If we insert this controller rods to the inside of the core, so that it keeps on absorbing all neutrons, and all the neutrons are absorbed. So if all the neutrons are absorbed, no reaction will be here. So it will get closed down, shut down. Right? But in ideal situation, what we do? We keep on inserting inside and outside the controller rod to control the number of neutron inside. More number of neutrons, more reaction, more heat. Less number of neutron, less reaction, less heat. Right? So that means, what is the other role of the controller? Not only to absorb the excess neutrons to control the reactions, but also to control the amount of heat generation. Control amount of heat generation. How the amount of heat generation will be controlled? That depends on the number of neutrons which are available. More number of neutrons available, more reactions, more heat generation. Less number of neutrons available, less reaction, less heat generation. So by adjusting inside and outside the controller rod, we can control the number of neutrons. By that we can control the amount of heat generation. And when we have to shut down the the reactor, we will absorb all the neutrons. The reaction will shut. What is the role of moderator? Moderator role is to slow down the thermal neutron, to reduce the speed of the neutron, so that they can be captured by the uranium nuclei. That is the role of moderator. Like heavy water as a moderator will slow down the neutron, whereas the boron or cadmium based controller rod will absorb neutrons. That's the difference. Clear? Any doubt? Any doubt with respect to this? So first you have to know what is a nuclear reactor, the components of nuclear reactor. Then it comes to the design. What we use as a controller, what we use as a coolant or fuel, or all those area comes into that. It's a very, very important part. See, remember that UPSC examination will not ask you what is controller, or what is coolant, or what is moderator. That will not be asked. That you would have studied in your science class in 9th and 10th standard. That is not the part of the UPSC exam. But why do you need to remember all this? Keep it at the back of the mind to understand the concept. UPSC will ask you more advanced question. That is on the 3 stages of nuclear power program of India. What are the 3 stages of nuclear power program? Right? How that is used there. You have to look from the application point of view. But yes, core area, theory part has to be at the back of the mind. Any doubt here? इनको पूरा दिखा दीजिए उस साइड भी, कंट्रोलर रॉड वगैरह जो है, फ्यूल और ये मॉडरेटर वगैरह. We'll now come to the 3 stages of nuclear power program of India. All of you have copied this? Any doubt you have? Have you copied it? Please copy this. Whatever I am teaching on the whiteboard, you have to copy down as part of your class notes. Diagram इनको दिखा दीजिए. Pawan is asking question. See, what is the advantage of PHWR when compared to BWR? Very good question. Pawan is asking a very good question. What is the advantage of pressurized heavy water reactor when compared to boiling water reactor? The advantage of using PHWR is that we can control more the production of heat because we are using the single heavy water both as moderator and coolant. So what happens in PHWR? You are not using two pipes, one pipe sending the normal water for a steam and another pipe sending the moderator to control the number of control the speed of the neutron. By using a single pipe which contains both moderator and coolant as heavy water, you are able to do the moderation at the same time absorption of excess heat. That is the one advantage of PHWR over the boiling water reactor. Second, number 2, boiling water reactor can be a problem if the amount of steam generation or cooling, let's say there is a failure of cooling. How the coolant goes inside the core of the reactor? That is pumped inside by a generator. There is a pumping machine. A pumping machine pumps the coolant inside the core of the reactor. Now imagine that the generator which pump the coolant material inside the core of the reactor and that machine fails because of earthquake or tsunami or any such area, such natural calamities. And let's say the reaction doesn't stop. Reaction keeps on happening, keep on generating heat energy, but the coolant fails. So what will happen there? It will explode like a bomb. What is we called as a meltdown. In Fukushima, in Japan in 2011, those reactors were boiling water reactor. Very important point I am telling you in the classroom. The accident which took place in Fukushima, Daiichi Nuclear Power Plant in Fukushima in 2011, they were boiling water reactors. They are older technology and steam is generated inside the core. And what happened? The coolant, the pipe or the pump which was sending the coolant inside the reactor, that failed. So there was no cooling and then excess heat generated, that caused the meltdown, leading to that accident, Fukushima disaster in Japan. Right? Another thing is that when you are using BWR, it requires a lot of water. Boiling water reactor requires more amount of water because you have to continuously feed the water, which becomes steam. The water becomes steam in the core, and then there is a loss of steam. So you have to continuously keep on supplying water. It consumes more water. On the other hand, in PHWR, pressurized heavy water reactor, the heavy water both as a coolant and moderator will keep on cycling inside the core because we are passing under high pressure, pressurized heavy water. The boiling point becomes higher. So as a superheated heavy water, it does the moderation and at the same time absorption of excess heat keep on happening inside there. The water which is generated, that is in another chamber, another steam generation chamber, and there water can be condensed and again can be recycled. So PHWR requires lesser amount of water there, right? There are a lot of advantages are there. Now Pratik is asking a question, what is the significance of PWR when ultimately normal water will absorb the heat to become steam to eventually generate it. That's what I said. Again, we can condense that water in PWR in the another chamber. We can again condense it back and again recycle it, reuse it, right? We can reuse it again. Another advantage is what? Radioactivity will be not there. The normal water which will get in contact will not be that much radioactive. Rishabh, boron have 3 valency and cadmium have 2. Then why they absorb the electron? Means they have to leave the electron there? Yes. I am not talking about electron. I am saying neutron. Just one second. Rishabh Bhai Sahab, neutron, absorption of neutron. मैंने यहाँ लिखा है ना, I have written here neutron. Have I written electron? Rishabh is asking, I'll read the question of Rishabh. Boron have 3 valency and cadmium have 2. Then why they absorb the electron? You are asking electron there. Means they have to leave the electron. It is not electron. Rishabh, you are asking the question electron. I am not talking electron. I am talking about neutrons. I am talking about neutrons, not the electron. पोथी पढ़ी पढ़ी जग मुआ पंडित भया न कोई. Right? Rishabh, where are you? Right? Chemistry part is okay. What you are saying, valency of 3 and 2 and all this, valency part is all right. Right? We are talking about nuclear phenomena. We are not talking about electrons and the chemical reactivity part of it. Right? Neutron will not remain inside the nucleus. Let me see here. What response you are writing? Let me read that. I am not able to understand. Why you are asking electron there? I am not able to understand. You are saying that, Rishabh Mishra is saying that neutrons will not remain inside the nucleus. So where the neutrons will remain? Where the neutrons will go there? Let's say when the moderate, this controller, see what happens is that you are confused. You have a lot of confusion. Why? That's what said, Poti padi padi jagmua, Pandit bhaya na koi. Why you are comparing with valency with the nuclear aspect? Nuclear phenomena is different from your electron phenomena. That is, you are mixing two things. You are mixing two things, that's why the problem is there. Right? Now understand here. Neutrons which will be absorbed by the, see what will happen there? Boron which will absorb the neutron. Which will absorb the neutron? The nucleus which absorbs the neutron, right, the boron or cadmium, let's say whatever may be that. Right, what is a boron? Boron has got which one? 3 and 5. 3 electron, that means 3 protons in the nucleus. Right? This is the thing, no? What is boron there? You said the 3 valency is there. 3 and 5, right? Atomic number 3, mass number 5. So what is the atomic number? Number of electrons outside, and that will be equal to number of protons, 3 protons inside the nucleus, and remaining 2 will be neutrons. So it will absorb the neutron, and what will happen there? There is also change of the neutron. Neutron doesn't remain that. Neutron will again break down into proton plus electron, right? And the electron goes in there, but that electron comes out of that. Okay, I am trying to make you understand. Just try to understand. Cadmium, this is a cadmium rod. Just try to understand. Rishabh, just try to understand. The cadmium, right? Cadmium which we are using as a rod, right? You said valency is 3, atomic number 3, right? What is the atomic number? Number of electrons outside the nucleus, right? And being a neutral atom, same number of protons have to be there in the nucleus, 3 protons. Mass number, let's say 5. So that means there are 2 neutrons in the boron. Let's say boron absorbs the neutron, it absorbs the neutron. So what will happen in the nucleus? Now it will have 3 neutrons and 3 protons. This is going to happen there. But then there is again the changes happen. It again makes the changes because we are talking about nuclear phenomena. If neutron breaks, what it forms there? It will form the electron proton, and then what happens? The boron will not remain as a boron. I have said, no, transmutation. There will be transmutation part of it, right? So let's say here, see the confusion what you have here. Let me take you to that one. I'll clear your confusion part. Let's say, for example, I am just giving you that. You will come to your part of it. When boron, let's say I am just doing the Google search, when boron absorbs, then it gets converted into something else, right? Absorbs neutron. Right? Let me write what happens. Now understand here. What happens when boron absorbs the neutrons? See here. I am reading out there. The neutron absorption reaction other than capture is a fission. The neutron absorbed by the target nucleus induces resulting compound nucleus to split into usually 2 parts. As part of this, what does boron do in a nuclear reactor? Now see here. By absorbing neutron during the nuclear fission, boron controls the rate of the reaction, can even slow or stop it. Right? Stop the reaction also there. Why is boron used in a controller rod? Now see here. The chain reaction controlled by boron control rod. Boron is non-fissile material. Non-fissile material, this means it will not undergo a fission reaction when bombarded with neutrons. When the boron absorbs neutrons, then the chain reaction will slow down due to the lack of neutrons producing reaction there. Why is boron a neutron absorber? Now look at here. Right? What is the here 5 and 11? Let's say this is boron 5 and 11. Atomic number 5, atomic number 5, mass number 11. Now look at here. Boron is another common neutron absorber. Due to the different cross section of boron, boron 10 and boron 11, these are the mass number. Materials containing boron enriched in 10B by isotopic separation, the frequently used there. The wide absorption spectrum boron makes it suitable for a neutron shield. The atomic number is not 3, let me correct myself. The atomic number of boron is 5. Mass number, there are 2 isotopes, maybe boron 10 or boron 11. Right? That can be there. So boron makes it there. Now see here. Why is boron a good at absorbing neutron? See here, this is given. It is a boron 10. What we use a nuclear rod? We use boron 10, 510. Boron 10, that is good neutron absorber. Boron 11 has a low cross section for neutron absorption. Now what is it? The size of the nucleus isn't, tell me now, so what happens? It absorbs there. Can you see the reaction, this reaction? So there is change in the nucleus part of it. Atomic number remains the same. Is 5 is the atomic number of boron, and boron is the 2 isotope. What type of boron we use in the nuclear reactor? We use the boron 10. It is able to absorb neutron, become boron 11. 11 is the mass number. Right? So see here what's given here. Activation energy of the reaction. Now what is happens here? See what is given here. Boron 10 has 5 neutrons while boron 11 has 6 neutrons. And boron 11 is more stable. So by adding a neutron, we are pairing up the neutrons there. So let me come to the whiteboard here. See here. So what is used here is that I'm using the whiteboard here. The boron rod is used there, 5 atomic number and mass number is 10. इसको whiteboard दिखाइए आप. Others in the classroom, don't worry about it. Rishabh has a scientific bent of mind, so I am explaining here. Not very important for UPSC exam. But since if I will not give reply to the question, then Rishabh will not feel good that sir has not answered the question. So whatever your query comes, it's my duty to give you the answer. But rest of the class, cool down. Don't worry. UPSC is not going to ask you nuclear science. You don't have to become nuclear scientist. You are going to become an IAS officer. So now see here. So when it absorbs neutron, it converts into this one. Right? Here, what happens here you have what is the atomic number? 5. Number of electron equal to number of protons. So how many number of neutrons are there in this one? Number of neutron here is 5. And when it absorbs the neutron, the nucleus absorbs the neutron, it becomes what? How many number of neutrons will be here? In this case, the number of neutrons will become 6 because mass number 11. So the boron rod, which is made up of this isotope, which isotope? 5b10, is able to absorb neutron and convert into boron 11. Right? So this neutron goes where? To the nucleus. All right. So anyway, we will stop the class here because Rishabh, if you are more interested to learn more nuclear science and all, please read the physics book or whatever the book you want. But it is not very important for UPSC exam. Right? For rest of the class, you should be chilled out. Because the borons, he asked that why boron valency, this and that, he asked that. So that's what I explained here. We are talking about nuclear phenomena, we are not talking about a chemical reaction. Right? Clear there? So anyway, I will stop the class here because already 4:30. Now your question is there. Your assignment question, let me write the assignment question. ये बंद कर दीजिए light. Your assignment question is that discuss nuclear reactor technology. Discuss nuclear reactor technology with its main components. Now, second part of the question is that differentiate between boiling water reactor BWR and pressurized heavy water reactor PHWR. You have to answer this question in 150 to 200 words. Ten marks question. So I am giving you a homework assignment here. Discuss nuclear reactor technology with its main components. Differentiate between BWR, boiling water reactor, and pressurized heavy water reactor. You have to answer in 150 to 200 words, 10 marks. So we'll stop the class here. And the next class will continue with the next class topic will be, let me write the topic of next class. Next class will continue with nuclear science and technology. We'll discuss about India's 3-stage nuclear power program. India's 3 stages of a nuclear power program, atomic energy program. Right? We are going to discuss that. And then we'll study about the applications of nuclear technology like radioisotopes in agriculture, radiation technology into agriculture, food, nuclear medicine, environment, energy, all those will come to applications of nuclear technology, nuclear science and technology in other fields, right? Like medicine, healthcare, agriculture and all we'll study. That is the topic of next class. Once we complete the nuclear science and technology, we'll move to the defense topic. Clear everybody? Well, next class, India's 3-stage of nuclear power program, we'll discuss all that and then application of nuclear technology in other areas. So we'll stop here. Thank you everybody. Thank you.